Maylin Ignacio. I'm Christina De Ocampo. I'm Chris Kubanggang.
I'm Marta Paligado.
We are Group 3! So guys, we would like to discuss to you the plate tectonic theory and evidences of plate movements. Let's listen,
Let's watch.
let's understand, and let's learn!
Plate tectonics. The theory of plate tectonics is a scientific theory that pieces of the Earth's lithosphere are slowly moving and creating the Earth's landforms. Plate tectonics is an expansion over the previous theory of continental drift proposed by Alfred Wegener in 1912. Wegener correctly identified that the Earth's landmasses were moving, but there were some flaws in his theory. For example, he proposed that the continents themselves were moving and not the underlying plates that were in motion. He also believed that the motion of the continents was due to the Earth's rotation. And yet, the theory of plate tectonics represents a fairly young science. The father of plate tectonics, Alfred Wegener, proposed continental drift in 1912, but was ridiculed by fellow scientists. Alfred Wegener, or Alfred Lothar Wegener, was a German meteorologist, geophysicist, and polar researcher. In 1915, he published The Origin of Continents and Oceans, which outlined his theory of continental drift. So there are presently 7 major tectonic plates. Tectonic plates fit tightly together, so movement pushing plates together or farther apart has become apparent over time. The boundaries of tectonic plates are repeatedly locations of earthquakes, volcanic eruptions, tsunamis, and the formation of mountain ranges or deep trenches as plate motion releases energy or pushes crust upward or downward.
And these are the 7 major tectonic plates. First is Pacific Plate,
Second is North American Plate.
the third is Eurasian Plate, and fourth is African Plate,
Fifth is Antarctic Plate.
the sixth is Indo-Australia Plate, and last is South American Plate.
Number 1. Pacific Plate. The Pacific Major Plate is the largest, which underlies the Pacific Ocean. Specifically, it stretches all the way along the west coast of North America to the east coast of Japan and Indonesia. Number 2. North American Plate. The North American Major Plate not only contains the continent of North America but also part of the Atlantic Ocean. Number 3. Eurasian Plate. The Eurasian Major Plate consists of most of Europe, Russia, and parts of Asia. This plate is sandwiched between the North American and African plates on the north and west sides. Number 4. African Plate. The African Plate contains the whole continent of Africa as well as the surrounding oceanic crust of the Atlantic Ocean. Oddly, it looks like a larger boundary of the African continent itself. Number 5. Antarctic Plate. The Antarctic Plate holds the entire continent of Antarctica, including its surrounding oceanic crust. This plate is surrounded by parts of the African, Australian, Pacific, and South American plates. Number 6. Indo-Australia Plate. The Indo-Australia Plate is a major plate combining the Australian and Indian plates, but they are widely considered to be 2 separate plates. Number 7. South American Plate. The South American Plate is a major plate that includes the continent of South America and a large portion of the ocean from the Atlantic Ocean. To fully understand the theory of plate tectonics, let's watch the video first.
Earth is a remarkable piece of real estate, and a busy one at that. From ever-changing weather patterns to the hustle and bustle of city streets, our planet is in a constant state of motion. However, if we take a look just below the surface, we find that things are always moving below our feet as well. It's called plate tectonics, and it's how the continents were formed and reformed and reformed. But before we get to that, Let's dive underground to learn what our planet looks like from the inside out. Our Earth is made up of layers, and there are two types of layers we need to learn about in order to understand plate tectonics: the compositional or chemical layers and the mechanical layers. We could spend an entire session on what makes both of these types of layers unique, but for this lesson we're simply going to provide an overview. There are three primary compositional layers to the Earth's surface, and these are probably the ones you're most familiar with: the crust, the mantle, and the core. It's important to understand that the compositional layers refer to the materials or elements the Earth is made of. However, if we take a look at how the inside of the Earth behaves, we can divide them even further into mechanical layers. Starting from the outside working in, the lithosphere is the outermost layer of the Earth, which contains the entire crust and the topmost layer of the mantle. The asthenosphere contains the same materials as the top layers of the mantle, but the pressure and the heat are increased. It's not exactly a liquid, but it does move like heated rock, so you could say it's somewhat fluid. The mesosphere is next. At this level, the pressure is really starting to build, which restricts the molecule's ability to move, thus making it very, very rigid. Past the mesosphere is the liquid outer core. Extremely high temperatures melt the metals contained in this layer into liquid form. Think flowing rivers of lava, and you'll have a pretty good idea of what the outer core is like. And finally, we reach the solid inner core. Just like the liquid outer core, the inner core has extremely high temperatures and is composed of mostly metals, which might lead you to ask, why isn't it liquid as well? The answer is pressure. There's so much pressure at this depth that even though the temperatures are beyond the melting points of the metals contained in the inner core, the high pressure essentially squishes everything down into a solid. Now that we know a bit more about the composition of the Earth, let's move on to plate tectonics. Let's start with the history. In the early 1900s, a scientist named Alfred Wegener noticed that the coastlines of several continents looked like they fit together, similar to puzzle pieces. He believed that around 200 million years ago, all of the continents were joined together in one large supercontinent that he called Pangaea, which is Greek for all the Earth. Over the course of millions of years, Pangaea broke apart into the continents we know today, a process he called continental drift. Although his theories explain quite a bit about the origins of the Earth, scientists at the time weren't exactly impressed and initially dismissed his ideas. Fast forward to today, and Wegener's concepts are the basis of the modern-day plate tectonics theory. So what exactly is the plate tectonics theory? Well, it states that the Earth's outer mechanical layer, the lithosphere, is divided into large continent-sized plates that are constantly moving. How fast are they moving? Pretty slowly, actually. Around 1 to 2 inches per year, which is why it was so hard for scientists 100 years ago to wrap their heads around the idea. So what changed their minds? Well, a few natural discoveries in the 20th century made Wegener's theories seem more plausible. For example, in the 1950s and 60s, scientists discovered heated magma rising up through cracks in the oceanic crust called dikes, which is how new rock or new land is created. This realization that our planet is always reforming and reshaping itself from beneath lent credibility to Wegener's theories. Point Wegener. Not long after, scientists started plotting the location of earthquakes and volcanoes around the world and observed that the location of those events followed a similar pattern to the outline of the plates Wegener proposed. And then there was the fossil evidence. Fossils of tropical animal and plant species have been found in Africa and other places on Earth that are less than tropical. One plausible explanation was that Africa was once part of a larger continent that was home to these tropical plants and animals. Remember Pangaea? So in light of all this evidence, the scientific community started thinking maybe this Wegener fellow was actually onto something, which led to the development of our modern-day plate tectonics theory. So now that we know the history, let's dive a bit deeper into how it all works. According to the plate tectonics theory, these massive lithospheric plates are all moving in different ways, and how they interact with one another can have a huge impact on the Earth. Where these plates meet are called boundaries, and there are three kinds. Convergent boundaries occur when two plates are moving towards one another. Transform boundaries occur when two plates are sliding past one another, and divergent boundaries occur when two plates are moving away from one another. Let's take a closer look at what happens at each of these boundaries. As we said, convergent boundaries are when plates are moving towards one another. When the two plates collide, a couple of things can happen. One of the plates will dive under the other plate. It's usually the heavier, denser crust that dives under the lighter crust. This creates what is called a subduction zone. And the deeper under the Earth's surface that plate goes, the more pressure it creates. That pressure, coupled with a high heat, causes the crust to melt, forming magma. The magma presses up towards the surface, and voila, you've got a volcano. An example of this is the Ring of Fire, which is an active ring of volcanoes that encircles the Pacific Ocean. The other thing that can happen when two plates press into one another at a convergent boundary is the rock above the boundary will be lifted up or folded and form mountains. Ever hear of the Himalayas? That's an example of two tectonic plates colliding. And because the plates continue to move, the peaks in this mountain range continue to grow. For example, Mount Everest, which currently measures around 29,000 feet, grows around an inch every year. So as you could imagine, it takes thousands of years for these mountains to form. But although movement at convergent boundaries is usually gradual, as pressure underground builds, the impact above ground can be quick and violent. Fast movement or slipping of the land can result in earthquakes either above ground or under the ocean. And convergent boundaries aren't the only type of boundary that can result in earthquakes. At transform boundaries, the Earth's plates are sliding past each other in opposite directions, which creates a crack or fault in the Earth's crust. As the plates try to move, they rub against one another, resulting in the building up of pressure. If the plates are stuck for a long period of time, the pressure will continue to build at the fault line until eventually it releases, resulting in an earthquake. The San Andreas Fault System is one of the largest transform boundaries in the world, which is why that area has more than its fair share of seismic activity. That just leaves divergent boundaries. Like we mentioned before, divergent boundaries occur when plates are moving away from one another. Either the space between the two plates widens and becomes a large crack or rift, such as the East African Great Rift Valley that runs from Lebanon to Mozambique, or if the space between the two plates is under the ocean, where the crust is thinner, magma oozes up from the Earth's mantle and fills the space. This is called seafloor spreading. The Mid-Atlantic Ridge is an example of where seafloor spreading has occurred. The crust under the ocean pulled apart, allowing magma to fill the space between, creating the tallest and longest mountain chain in the world. So in review, the plate tectonics theory is based on concepts first proposed by Alfred Wegener in the early 20th century. It states that the Earth's outer mechanical layer, the lithosphere, is divided into large continent-sized plates that are always moving, leading many scientists to believe the continents we know today were once part of a supercontinent called Pangaea. These plates move 1 to 2 inches per year. Where they meet is called boundaries, and there are 3 different types. Convergent boundaries, where plates collide, transform boundaries, where plates slide past one another, and divergent boundaries, where they move apart. Volcanoes and mountains form at convergent boundaries. Earthquakes and tsunamis can occur at both convergent and transform boundaries. Fissures and large cracks in the surface occur when 2 plates move apart at a divergent boundary. And seafloor spreading occurs at divergent boundaries located at the ocean floor. So that completes our lesson on plate tectonics.
So guys, let us talk about the evidences of plate movements. Do you know what are the evidences of plate movements? So these are the evidences of plate movements. Actions at the edges. So why is there so much tectonic activity? Earthquakes, volcanic eruptions, and the formation of mountain ranges. In the western United States compared at the east, tectonic activity commonly occurs along the boundaries of moving plates. The Pacific coast of the United States coincides with plate boundaries and thus has earthquakes, volcanic eruptions, and developing mountains ranges. The Atlantic and Gulf Coast, though initially formed from plate boundary activity, are now far from any plate boundaries and accompanying tectonic events. Most mountain ranges are long and narrow because they form at plate boundaries or hotspots. The largest mountain range on Earth is the system of mid-ocean ridges, a line of underwater volcanoes formed on the seafloor as plates diverge. Plate divergence sometimes rips a continent apart, forming long mountain ranges separated by rift valleys. Where plates converge along an active continental margin, the one with thin oceanic crust descends or subducts beneath the continent, forming two parallel mountain ranges. One is a coastal range consisting of material squeezed up out of the sea, the other a volcanic chain farther inland above where hot water rises from the descending plate. The highest mountains on Earth, the Himalayas, are forming where thick blocks of continental crust, India and Asia, collide as a result of plate convergence. Sheared up mountain ridges and valleys form in a narrow zone where one plate slides past another at a transformed plate boundary, and the mountain chain of volcanoes forms where a plate rides over a hotspot. The volcanoes get older and lower as the plate moves them away from the hotspot.
Volcanic eruption. Volcanic activity occurs about place in Earth where pressure, temperature, and the presence of water compared to mere rock. There are two means where Earth material melt. 1. Hot matter raise and decompresses. 2. Water flow toward hot rock. The first type of melting occurs at divergent plate boundaries, mid-ocean ridge, continental fit zone, and a hotspot where mantle beneath plate is hot but remains solid because it is under great pressure. As the hot mantle raising sudden drop in pressure, case melting much as a talking. The lid of a pressure cooker case superheated water to flush to steam. The second mechanism results in the volcanism at convergent plate boundaries. As one plate dives subduct beneath the other, it heats up the released hot fluid, similar to way we sweat when you get hot. Fluid monthly water, used waiting for hot rock in pot, and casing some of the rock too.
Earthquake. Two things are necessary in the earthquake. To occurs one motion within the earth that stress and deforms material, and two material that deforms by breaking rather than flowing moving plates of called brittle. Lithosphere produce most earthquakes, especially where they are contorted and grained against one another along their boundaries.
To fully understand what are the evidences of plate movements, let's watch the video first.
In this lesson, we are going to discuss the evidence of plate movements. At the end of this video lesson, you should be able to explain the different pieces of evidence of plate movements. Since Pangaea existed during the Permian period, one important evidence that may support the continental drift theory is the field of paleontology, or study of ancient life. Paleontologists needed to look for pieces of evidence of life on the locations that are said to be connected. One of the fossil evidence is Glossopteris. Since a plant as large as Glossopteris cannot move and cannot pollinate on the long range, it is believed that the presence of this plant in South America, Africa, Madagascar, Antarctica, India, and Australia is possible because of the connections of these places. Its pollinators might have been able to traverse these locations easily. Another fossil evidence is the Mesosaurus. The Mesosaurus is a freshwater lizard which was found in South America and Africa. Because it is unlikely that the Mesosaurus could have traveled broad stretches of open saltwater, their geographic distribution provided paleontological evidence supporting the hypothesis that these two continents were once joined. This map shows the Mesosaurus Sea, the freshwater habitat of the Mesosaurus. The Cyanognathes is a mammal-like reptile that resembles the present-day dog, which give its name and meaning of dog jaw. It is a fossil found in Africa and Argentina, which is a part of South America. The Lysosaurus, also known as the shovel reptile, is a herbivore reptile whose fossils had been found in Africa and India in the mid-1960s. By the end of 1960s, Lysosaurus fossils were also recovered from lower Triassic rocks in Antarctica's Transantarctic Mountains. Combining the paleontological evidence discussed, it is found out that these fossils can connect the continents based on their distribution patterns. Their distribution patterns would result to disconnection of the continents, thus giving us the second evidence of plate movements, which is the apparent fit of the continents. The coastline of continents, even if we do not take into consideration the distribution pattern of the organisms found by paleontologists, will still fit together like puzzle pieces. It is not only on Gondwana in which the continents fit together perfectly. This is how the continents are believed to have appeared before as one big puzzle. To say that this is not a coincidence that these continents have coastlines that fit together, geologists also look into the parallel mountains of the coastlines of neighboring continents. Particularly, geologists look into the Appalachian Mountains in North America and compared it with the mountains parallel to it in Africa. Geologists found out that these rocks in the two mountains are similar in composition and layering order. The same methods were done to compare the mountains in Greenland, and geologists found out that the mountains may really be connected because of the same finding. This means that similar order, arrangement, and structure of the rock layers and mountain ranges on opposite sides support the idea that continents are connected before. This is what we call rock and mountain correlation. This is one information which we can get from rocks. Another evidence from rocks is the magnetic reversal. Remember that the Earth acts as a big magnet. This means that the minerals in the crust which are pushed out of the ridge are attracted to the magnetic pole of the Earth. Magnetic reversal shows the spreading of the seafloor, and we can see the polarity of the magnetic field of the Earth in rocks. Particles in it get frozen in the direction of the magnetic field as magma cools. Scientists can see the polarity of the magnetic field at the time that the rocks were formed by looking at these particles. Another information which we can get from rocks is glacial striations. When large boulders are pulled under glaciers, glacial strips are left. They scrape the underlying surface as they pull along, forming grooves parallel to the glacier's direction of movement. This gives us the next evidence. By arranging the glacial striations, geologists were able to determine the movement of the continents as they drifted away from each other. Using the glacial striations directions, Wegener showed that the glacial striations in South America, South Africa, India, and Australia actually mean that all glaciation experienced at about the same time. The striation points to continental glaciers originating in various locations in their current positions. Striations, however, point to one continent by aligning the continents. Alfred Wegener was well aware of such climatological mysteries as a meteorologist, such as the remains of temperate climatic trees that can be found under the polar ice. From this, he started to map worldwide rock and fossil data distributions that suggested tropical, desert, and polar climates. From this, he found that continents displayed signs of many climates being felt. Some of the most important climate data come from the South American, African, Indian, and Australian continents. All these continents display signs of glaciation in the past. To end this lesson, let us review again the following pieces of evidence of plate movements. Fossils show the connections of the continents which comprise Gondwana. The continents can fit together like puzzle pieces. Lastly, pieces of evidence from rocks include mountain correlation, magnetic reversals, glacial striations, and paleoclimatology. And that ends our discussion on evidence of plate movements.